This lecture is about the stochastic finite elements, which is a tool for uncertainty quantification. The lecture is divided in 4 parts. In the first part, we're going to see how a stochastic PDE becomes a stochastic algebraic equation, which is the same thing we do with standard deterministic PDEs or boundary value problems with finite elements. We transform them into linear or nonlinear systems of algebraic equations. Second part is dedicated to explain how to operate with stochastic quantities, which are random variables. Then we're going to see how to solve these problems based in stochastic equations with 2 families of solvers, which are the Monte Carlo solvers, very standard ones, and polynomial chaos, which are intrusive and non-intrusive, respectively. Then we're going to see the Calcul-Levy decomposition, which is actually a variant of PCA, of principal component analysis, which aims at reducing the stochastic dimension of these problems. Recall that we have seen that Bayesian updating was used in order to characterize, using available data, the parametric input of some problem as a random variable. Then these parameters can be used as input of a new model that provides a solution and some quantities of interest of this solution, which are stochastic. What we are going to deal with in this lecture, uncertainty quantification, aims at characterizing the stochastic behavior of this output. The first part of the lecture is about how do we create a stochastic PDE and how this stochastic PDE becomes a stochastic algebraic equation. First, we're going to see a motivation problem. Then we're going to see how finite elements transform PDEs into algebraic equations, which is kind of recall or reminder of what finite elements do. And then we are going to properly address the question of how a stochastic PDE becomes a stochastic algebraic equation, which is kind of natural consequence of these 2 factors. An interesting example of a problem in which stochastic finite element may play a role is automotion. So, standard problem in automotion, which is the mechanical characterization of some component, like for instance a B pillar, which is one of these intermediate parts of the car that support a lot of mechanical stress. So the idea is try to characterize the behavior of some element like this one, and try to get the answer in any of the possible scenarios. Typically, a car is a very complex structure, so many car manufacturers like Volkswagen have created benchmarks, and typically we address the exploratory problems in simple cases like the one we're seeing here, which is how a impactor acts upon a beam that represents the behavior of this B pillar. The problem is that many inputs, like for instance the material behavior of the parameter of the parameters characterizing the material behavior, may vary a lot in different circumstances. So the idea is that we don't know exactly which is the type of material that we're exactly using manufacturing these pies, and it is very important to having the range of possible solutions corresponding to all these variation. We are uncertain in the input, and we have to characterize uncertainty of the output. So we go beyond determinism. The idea is that many uncertain factors affect the behavior and the response of our device, and most typically uncertainty is collected in these cases of automotion mechanical problems in the thicknesses, so we are not sure about the nominal thickness of the different plates, in the material properties, for example, I just shown, in the loads, so not only the force, but also the speed of application of the force, the acceleration, the frequency, and then the geometry as well. Not only because the shapes may be different, but also the dimensions and the location, for instance, of the loads. And we have to characterize quantities of interest, which in this particular case of the benchmark problem results in some average stress or plastic deformation in this zone, which is which is particularly critical in this structure because there is an adhesive contact zone. And the idea is how much is this quantity, this stress, average stress or average plastic strain, but not as a deterministic value, not as a number, but as a random variable. So we are going to characterize an average, mean, but also standard deviation, and we may also, and that's the idea, we may also characterize which is the probability of exceeding some critical value, which is actually what matters for an engineer. Standard or deterministic finite elements consists in solving a differential equation, a PDE, with its boundary conditions, which is also called a boundary value problem. For instance, the standard one, which is the mechanical equilibrium. The idea is that we can write it in the strong form in which we account for second derivatives of the initial unknown, or also in a weak form, which is typically stated in that way, which we have to find u such that it fulfills this equation, being a bilinear form and L a linear operator, for every v. So u is the test function and v are the trial functions. So the idea is that once we select all these functions in a discrete finite dimensional space that corresponds to a mesh, for instance, the mesh of this plane here, then we end up by having an algebraic system of equations. The equations are linear if the original problem is linear, and nonlinear if the original problem is nonlinear. So we end up by having something like that, which is a linear system of equations, linear, with some stiffness matrix K, some force vector F of nodal values, nodal forces, and as a known, we have the nodal vector of displacements. How it becomes stochastic? As we said before, many input parameters of the problem may be stochastic. What happens? That means the resulting solution U depends on every point in the space X, but also some stochastic dimension theta. So the idea is that as the input problem becomes stochastic, because many of the input parameters are stochastic, instead of having a deterministic linear system of equations like k times u equal f, we have something which is very similar, but the matrix becomes stochastic. So the matrix has an average, standard deviation, has a distribution of probability. The same happens with the vector of forces. So therefore, we have to solve this problem. This problem, u, solution. In this problem, the solution is u, which is also stochastic, as resulting of having stochastic operation. So the goal of a stochastic finite element is discretizing in the standard way, but finding not only a number, but a distribution of probability. So the PDF of u, or any quantity of interest that depends on u, and some moments, average, variance, or some percentiles, as I said before, the probability of exceeding some critical value, which is for most of the engineers what matters. And in order to do that, we're going to see some analytical strategies, which are mostly intrusive, but also the most naive one, which is the Monte Carlo strategy, in which the finite element code is acting as a black box. The second part of the lecture is about operating with stochastic quantities, which are random variables. And we're going to see how to characterize analytically stochastic functions and their output, how to provide numerical approximations, and use the Monte Carlo idea. let's assume that we have a stochastic variable x, which is characterized by the probability density function fx equals more 1 and the cumulative distribution function capital Fx. Recall that the cumulative density distribution function is the probability for the variable, the random variable capital X to be lower than any value small x, or the integral of the density function from the lower possible value x min to the actual x. In this definition is implicit the fact that the capital F is the integral of small f, and vice versa, that the PDF is the derivative of the cumulative distribution function. So now the question we want to deal with is, imagine that y, a new random variable, is the image by a mapping phi of x. And assume that for a moment that the phi is a regular mapping, so it's invertible, it's bijective. So it's very easy to characterize the cumulative density function, so cumulative distribution function of y by the usual definition, and you conclude, assuming that phi is a mapping, that capital Fy is capital Fx composed by the inverse of phi. So if you take derivatives out of it, you can compute the PDF of y, which results in this more or less complex expression that when you use abuses of languages, so you identify x and y corresponding to the mapping phi, then it boils down to this very simple expression saying that the density function of y, what we are going to compute, is the density function of x divided by the derivative of the mapping phi with an absolute value. What happens when we have two input variables and one output variable? So phi is equal, z is equal to phi of xy. And in this case, of course, phi cannot be a mapping anymore because there is no possible bijection among a two-dimensional space and a one-dimensional space. So we assume that the input xy is characterized by some joint distribution f of xy, and we want to characterize the distribution of the output, so we use again the definition of the cumulative distribution function capital F of z, which is the usual definition, and we can write it as the integral in a subdomain omega z that depends on the value in which z, in which we want to approximate to compute the cumulative distribution function fz of the original distribution function fxy. What is this omega z? Omega z, it is indicated here. Omega z is the set of original points xy such that phi of these points is lower than z. So we want to compute the probability of being capital Z lower than some value z, and this is the probability of xy, the original points, of having phi of xy being lower than z. So that looks logical. So this is a definition of the cumulative distribution function of z. And then when we take derivatives, and the derivatives here are complicated because we are differentiating with respect to a variable which affects not the function itself, but the definition of the domain of integration of in which we compute it, then we end up by having an expression like this one, which is corresponds very much with what we had in 1D, because it is the integral in the points, the boundary of omega z are exactly the points in which phi is equal to z of the original density divided by the module, the norm of the gradient, which is, as we said before, the inverse of pi. So how can we characterize other quantities of the transform random variable? For instance, the mean, the average. So we assume that phi is analytically known. What is the average? The average is the integral of y times the probability density function of y. We apply the transformation we just got, and we understand that this is, you can integrate it in the original domain of x by multiplying the phi of x and the original PDF of x. The same applies for more complex setups in which, for instance, z is equal to phi of xy, because the average of z is also the interval in the original domain omega where x and y lies of phi of xy times the density function of xy. And the same with the square of z. We have just to integrate the square of phi. So that allows you to compute analytically. If you know phi analytically and fxy analytically, you can compute both the average of the variance, because the expectation of z squared together with the expectation of z allows you to compute the variance. Problem is that most of the cases you don't know the analytical expression for phi. So what you have to do is either integrate it numerically. That means that you have to evaluate phi in many points and then sum all the contributions of these points with a standard numerical quadrature, or you have to go to the very well-known Monte Carlo method, which comes from the gambling in Monte Carlo. It's plenty of casinos. It's about gambling. Monte Carlo is about gambling, and the idea is very simple, is that you generate a set of realizations of x and m number of Monte Carlo realizations as large as possible. You generate them following the input distribution fx. So if x is a normal variable, you concentrate most of the realizations around the Gauss bell, and then you apply phi to all these discrete points. So phi you don't know analytically, but you are able to apply phi to every value you want. So you do that for this large set of variables and m, and then you have a set of data, a set of values of y, which follow the distribution of y, which you don't know, but you can perform statistics out of it. You can compute the variance or the mean, or you can compute a histogram, and you can approximate fy, the PDF, as the histogram of all this data. The third part is about intrusive and non-intrusive method, responsor phases, and polynomial chaos. The definition of intrusive or non-intrusive is a little bit fuzzy, but in essence, it comes back to the idea of requiring to modify the finite element code or not. So if you can use your finite element code as a black box and just call it as many times as you want, but you don't have to touch it inside, then you are non-intrusive. And this typically corresponds to the methods in which you evaluate the many instances of the input variables, but you don't perform analytical transformations of it. So Monte Carlo is the typical case of being non-intrusive. And the opposite is not very efficient, because it requires, in order to converge properly to the good stochastic properties of your output distribution, it requires a large number of Monte Carlo thrones or Monte Carlo evaluations. Conversely, the methods, and we are going to see polynomial chaos as an example of it, in which you treat analytically the distribution of probability of the input and the output, are intrusive in the sense that very often they require to modify the finite element code and to perform very specific operations inside the code. The responsor phase is a concept that allows you to be much more efficient while keeping using the Monte Carlo idea. And the idea is very simple, is Monte Carlo requires to evaluate phi, which is the function that relates the input with the output, many times. So it requires to call the finite element code many times. That's what expensive thing in the crash worthiness of the car. So each time you want to perform an evaluation for a different value of the input parameters, you require waiting 1 day, or at least, or 1 day of computation in a large cluster, and that's what happened in the car manufacturers. So imagine that instead of doing that for, I don't know, 100,000, 1 million realizations, that would be feasible. Instead of doing that, instead of doing that for a very large number of Monte Carlo films, you do it for a training set, a representative sample NT, which has to be much lower than NM. And then you get a number of responses associated to these points. And what you do is to fit a function doing any kind of functional approximation, polynomials, splines, kriging, whatever you want to use, in order to approximate your function phi by a function phi star. That's what we call a response surface, an approximation characterized with the usual functional approximation techniques of phi. Once you have built this phi star and you rely in that it represents properly phi, so it's a good approximation of phi, then each time that you want to generate a new Monte Carlo sample, it's extremely efficient and economical. You don't need to wait 1 day, you need to wait a fraction of a second. So that's very interesting. And it still keep the non-intrusive character. That's interesting, but of course it relies on the possibility of approximation this function phi by a function phi star with a small number of samples. Okay? So if this is possible, so if your function to be approximated is small, that's a very good alternative. Polynomial chaos is a strategy in which the output, the solution that depends both in the space and the parametric stochastic dimension, theta, is expressed in terms of a separated representation of some modes or unknowns that depend only on x, and some polynomials depending on theta. Typically, you choose the family of polynomials you prefer. In particular, in these applications, we are very inclined to use mid polynomials for reasons that we are going to see in a while. Obviously, you need an infinite term series in order to properly represent the variation of any possible functional dependence on x and theta. But here the assumption is that you get a proper approximation with a small number of polynomial chaos terms that we denote by NPC. If instead of a continuous representation of the displacement vector, for instance, ux, you get a finite element representation in which the space variance is represented by a vector of nodal values. The only thing you have to do is represent this vector u as a function of theta as a term of vectors that are independent of theta, so constant vectors, times the polynomials that describe the dependence with theta. So these Hermite polynomials that I mentioned before are the ones that allow you to represent in an optimal fashion the dependence of this type of functions, because they are orthonormal with respect to a weighting function W, which is precisely the Gaussian bell corresponding to the normal distribution. So since they are orthogonal with respect to weight, which coincides exactly with the PDF for some thetas, in particular for the thetas that are considered as normal distributions, then you may compute all the quantities in post-processing very easily. For instance, the average, the mean, the expected value of the product of two of these Hermite polynomials is precisely some constant that accounts for the size or the norm of these polynomials times this Kronecker delta, meaning that if the I and the j are the same number, you get some positive number here, but if they are different, you get a 0. So that's the orthogonality. The orthogonality results in a 0 average for the product of two different Hermite polynomials. So the average of one of them is just the product of psi 0, which is a constant vector times the constant polynomial, so times the proper psi, and that means that it's going to be h0 times the delta I0. So it's h0 for I equal to 0, and it is 0 for any other I. So that allows you to compute very easily the mean value of any vector represented by the polynomial Gauss expression, because it depends only on the first term, the u0. So the average, the mean value of the polynomial Gauss representation of your solution depends only on the first term, and the rest of the terms are not affecting the average. Of course, they do affect, for instance, the variance, because when you compute the expectation of square, so to speak, the matrix which results of computing U times U transpose, that's a matrix. It's a matrix that it is part of the matrix of variance and covariance. It depends on all the terms in your polynomial Gauss expansion, not only on the first one, but still is a term which is pretty easy to compute given the terms of the polynomial Gauss expansion. So now we know that this type of polynomial Gauss representation is useful in order to get quickly some statistics from the solution, but the question is how to obtain it, how to compute this polynomial Gauss representation of our solution. And the idea is that we're going to do something that is very useful or very usual in numerical methods, which is Galerkin projection, which is nothing very different to least squares projection. So the idea is that you have to weight the residual of your function by this quantity, which is the weighting function of, sorry, there is an x here, and the size, and then you integrate along theta for every k. So this is what we do here in order to compute the solution of this solution, and we start by a particular case in which we only account for the stochastic force term. So we take K as a deterministic matrix, and we assume that F is stochastic, so F depends on theta. We also assume that there is this time of polynomial Gauss dependence on theta. We weight by this dependency, and then the resulting weight in the residual, which is equivalent to weight in the left and in the right-hand side of the equation. And what we actually obtain is that due to the orthogonality, it results in an independent system of equations that all with the same matrix K, and you have to solve for each term of the right-hand side. Okay, so this is what happens when only the force term is stochastic. In the general case, both the matrix and the force term are stochastic. We are going to assume that K has a polynomial Gauss expansion. Again, we weight with the same weighting function, both the left and the right hand side. And then this time things are not as easy as before, because in the left hand side you get this type of expression with a double sum, and what goes inside this double sum is a matrix M, which is a linear combination of all the matrices that represent the polynomial Gauss expansion of the stiffness matrix K. And these new matrices are all coupled together in a large linear systems of equations that you can write as as it is written here. So you compute all the modes together, involving all the terms, all the modes describing the force term, and all the terms describing the stiffness matrix. So because they are used to compute this matrix capital M. Okay. So this is something that allows you to compute all the terms in U. So once you make up the system, you compute all the terms U in a row. That's just solving a linear system of equations, something similar, easy, and not too large, because it's the size of the original system multiplied by NPC. But the problem is that this system of equation is very far from what you can expect or you can find inside any finite element code. So this system is very intrusive. So you need to code something completely different of what you have in a standard finite element code. With the polynomial Gauss expansion, you have all these coefficients which allow you to explicitly account for the dependence on the stochastic dimension theta. So you don't need to generate any other Monte Carlo or any other type of strategy to characterize the function mapping theta into your solution. So this is exactly the goal of the polynomial chaos methodology, to avoid Monte Carlo or any other strategy that relies in evaluating many times the system to be solved. Of course, conversely, this requires solving this system of equation, which is very unusual in a finite element code, and that's why the method is intrusive. The last part of the lecture is about reducing the stochastic dimension. Not only because extending polynomial chaos to multidimensional setups is complicated, but also because the complexity or the requirement of a lot of Monte Carlo terms increases very much with the number of dimensions of the input random variable. So we look forward reducing the dimension. And the Kerguelen-Love methodology or theorem or expansion is a particular case of the principal component analysis we have seen in this course before, applied to the stochastic context. So in order to present it, we are going to assume that we have a stochastic field. So it's not just one stochastic parameter theta, but it's a different stochastic parameter theta in each of the points of the domain. So you have infinite number of random variables, but they are not independent. They have a correlation, internal correlation with different thetas. If you think in the theta being the Young modulus of your material, it can be different point to point, but if the points are close to each other, you expect having a correlation, and the correlation is going to fade out as the points are far away from each other. The idea of the Kerguelen-Love expansion is representing this theta as a function of x, which is random, it's a stochastic quantity, the sum of a field which is deterministic, which is going to be the average, and a sum, which is familiar for us in PCA, of amplitudes, modes that depend on x but are deterministic and non-stochastic or random, and some independent random variables. So the idea is that all the randomness of this expression lies in these guys here, the x's, which are independent. So in the different terms of the sum, the x's are independent. And of course, we're going to use, as we do in PCA, the eigenvalues of eigenmodes of a covariance operator. So typically, this is much easier to understand, in my opinion, when you look into a discrete case. So as we said before, it's not u of x, it's not theta of x, it's a vector of values of theta, which corresponds to different points in the domain, but a finite number of them. And then you have a matrix of variance of covariance that in the case of having a zero mean, a zero expectation theta, so if you think in a perturbation or a noise that changes your elastic modulus in different points of the domain, so the variance is exactly the expectation of theta times theta transpose. And recall that theta is a column vector, theta transpose is a row vector, so the product of these two vectors is a matrix. And you take the expectation of it and you get matrix C. Matrix C is a symmetric and positive definite matrix, so you can just diagonalize it, and we are going to use the usual notation of U as the matrix that changes the bases, lambda, the diagonal matrix containing the eigenvalues, and U being C symmetric can be thought as a unit matrix such that the transpose of it is equal to the inverse. So we change variables, we introduce a new variable, which is just the one that corresponds with the change associated with the U. So zeta equals Z equal to U transpose theta, or theta equal to UZ, is such that the variance of this new variable Z is exactly lambda. So this new vector is such that the variance is diagonal, so it's such that each of the components of the vector are independent to each other. So they are uncorrelated statistically. So we can represent the vector theta as a linear combination of the components of Z and the columns of matrix U. So this is the standard change of basis. And the only thing we do as an additional modification is that we normalize the z's, since the variance of each of the z's is precisely the lambdas, which are the value of the matrix, which stands for the matrix of covariance of the z's. We divide each component of the z by the square root of lambda, such that these new variables xi are also independent to each other, but they have unit variance. So we can express theta, again as here, it's a sum of the square root of lambda, which comes from here, the x's, and the vector u, which corresponds to the columns of matrix U. Okay, so this is a standard, pretty standard expansion or representation of vector theta in terms of the new variables chi. Again, chi are the only ones that are random here. And then, as we do in PCA, we realize that if the values of the eigenvalues are decreasing very fast, taking a reduced number of them is sufficient to represent properly the variance of the variable. So if instead of taking n, the full dimension of the problem here, we take a much lower number nkl, kl is standing for Karun-Love, we construct a reduced version of theta, theta star, which collects most of the information. So this is, again, the same principle as in principal component analysis. So this is what allows us to reduce the stochastic dimension. Exactly the same idea of PCA. The only thing that we have to note here is that this discrete form of the Karun-Love decomposition corresponds very much with the continuous one, the one that depends on x instead of being a vector that we presented at the beginning. So this one, recall, that has exactly the same structure as the one we have obtained with the discrete form. And again, in the one we did in the discrete form, this guy did not appear because we assumed that the average was 0, so this is 0. And we had exactly the same structure with the only, with a very important remark that this is what collects all the randomness. So the randomness of theta, which is expressed in terms of x. Here, it is separated. The randomness does not depend on x, and all the dependence on x is in the mu's, in the modes, and moreover, the ch's, the new random variables, are independent to each other. And this is what we're going to use in the assignment corresponding to this lecture.